right, welcome to Unit 2, Lesson 13. So we're going to start off our lessons by going over a question from previous EOGs. So I want us to make sure we're focusing on these test-taking strategies in math as well as science. This is a calculator active question, which means yes, you can use a calculator. And change the color of my pen so it shows up a little bit better. All right, so you always want to read our question carefully. Examine every answer choice. Label your answer. We're also going to label the question. Always check our work and X out wrong choices. So first, let's read our question. A poster on Cameron's wall is 24 inches wide and 18 1/4 inches high. On top of the poster is a 3 1/4 inch heading. What is the area of the poster without the heading? So it's always important to find those keywords, such as without, and box them. So without the heading. So we're trying to find the area of the poster without the heading. So this heading we are going to not include. So we're trying to find the area of this part of the poster. So we know that finding area, because we've gone over this, is length times width. To find the area, it's the length times the width. So our length is going to be 24 inches. So area is equal to 24 inches times our width. So you might be quick and go, I'm just going to multiply it by 18 1/4 inches. However, that's this without section. So we need to find this area right here. So hit pause on the video, and I want you to find out what is this width right here that I just marked in green. All right, after you have found that, you are going to multiply them. If you're struggling, let me show you. So we have 18 1/4. And we're going, that's the entire width of the entire poster. But we need to take off this heading. So we're going to take away or subtract 3 1/4. So in order to do that, these 1/4 right here and right here actually cancel each other out. Because a quarter minus a quarter means it's 0. So that's going to bring us to 18 minus 3, which is 15. So that is our width. So we're going to do 24 times 15. Go ahead and hit pause and multiply that out for me. So once you've multiplied that out, you should get 360. So we always want to check our work. We want to read our question again. What is the area of the poster without the heading? So we make sure we took off that heading. We have 15 times 24. And this is where you double check with your calculator. And let's see if we're correct. The answer is B. It is that 360. All right, so we're talking about tables and double number lines today. So by the end of this lesson, I hope that you can use a table to look at equivalent ratios. Remember that word equivalent means the same. So ratios that represent the same thing. That you can include a column labels. Those labels are going to be very important. We're going to talk about that. When you create a table, labeling things is always very important. And then you can explain why sometimes a table is easier to use than a double number line. So for a quick warm-up, I want you to find the quotient. Remember that word quotient means to divide. Quotient is divide. Product is multiply. Quotient is divide. So you're going to find the quotient. of each of these mentally. Go ahead and hit pause and work that out. So when we're dividing 150 by 2, there's a couple ways we can do it. We have 150 over 2. And so we're finding half of it. So I know how I work this out is I'll take half of 50. And I know that half of 50 is 25. Then I'll take half of 100. Because again, that's 100. And I know that is 50. And I'd add those together, and that's 75. Now, when we go to 150 divided by 4, there's a couple things you can do. You can use that we just did it by half, and we can just divide 75 by 2 to get 150 divided by 4. Or you can put 150 divided by 4. And you can work this out the same way. So, I might start with 100. 4 quarters of 100 is 25. And then half of 50, I know, is 25. And then half of 25 would be 12.5. And I know that because I know that half of 24 is 12. And half of 1 would be 0.5. So 12.5. I'm going to add these up, and I'm going to get 37.5. So now we're down to 150 divided by 8. Again, I can divide it out the same way. I think 150 divided by 8. I know that, half of 100 is 50, and then half of that is 25, and then half of 25, which is where we're going, would bring me to 12.5. So, and then I have my 50 divided by 8 is not even going to be a whole now. So it's going to be the same as half of 12.5. 6.75. And then we add these up. We get 18.75. Now we're going to locate these on the number line. So I want you to notice the pattern. Let me change my color. Patterns are very important when we're talking about math. So I want you to notice the pattern because we went 2, 4, 8. So we took 2 and then increased it to 4. So 2 is a half. So we have our 150 over here. We're going to divide that in half. We're dividing all of this in half. This is where 75 is. Now we have our two halves. We have the half on this side between 0 and 75, and then we have the half from 75 to 150. So now we're taking 150 and we're dividing it by 4. Well, 150 divided by 4, we're finding half. So we have 75. We found half of our half. Here, it's half of 75. So we're going to mark that halfway through. And that is our 37.5. Because it's half of the half. And then we're going to use that same pattern. Half of 37.5 is 18.75. So we're finding the half of a half of a half. Now that's a lot of halves. But if you notice the pattern, we cut in half, cut in half, cut in half. Now we're cutting each section in half. And this is 18.75. And here are our answers. Double check our work. All right, so today what we are working on is thinking about tables. So our first question we're going to look at is we saw that Han can run 100 meters in 20 seconds. Remember we talked about distance over time. Kind of like that miles per hour. Miles per hour. This would be meters per second. Per second. Meters per second. So he went 100 meters in 20 seconds, but we need to find that per second. Han wondered how long it would take him to run 3,000 meters at this rate. So he made the table of equivalent ratios. Let's look at this table. So we know he ran 100 meters. So I'm going to look for meters. Well, there's the 100 meters. And then the seconds. There's the time. So looking at this table, do you think that it is a good table? So in this, the first three rows are great. We have 20 to 100, 10 to 50, 1 to 5. You notice we cut them in half. We went 20 to 10, and then 100 to 50. And then we found, by removing that 0, we have 1 to 5, 1 to 5. But let's look at this fourth row. I don't agree that the fourth row is correct because we're talking about our meters. That's not our meters. We have our seconds and our meters, right? 20 seconds to 100 meters. 50 meters in 10 seconds. 1 second is 5 meters. This is why it's always important to label. Label. Everybody label. Always label. So our labels here are supposed to be time in seconds to distance in meters. But see, this 3,000 really should be right here. So, no. The first three are correct. It's hard to write on my screen. So complete the last row with the missing number. So we'd have to move that over here, right? And the empty cell should be 15,000. Hello, how did you find that out, Miss Nishikawa? Where did you get 15,000? How did you do that? That's a big number. So, in order to find it, we'd have to, let's look at our table. We're just going to do our bottom rows. We have 5 meters for 1 second, because here's our time and our distance. 5 meters for 1 second. And we need to find out the 3,000. Because we got to correct his error there. So 3,000 is going to be multiplied. It's 3,000 meters. Sorry, my computer's freezing. So it would be 15,000 if it was incorrect. So 15,000 seconds. We get that by multiplying or dividing. What do you think? Pause it. Do you think we're going to multiply or divide? So we're going to multiply 5 times 3,000, which is 15,000. So let's look at number 3. What question about the situation does this number answer? And in the case of up here, let me see if I can erase this. We multiplied 5 times 3 because we're crossing. Whenever you cross on your diagrams, you're multiplying. And that's where we got 15,000. But in this case, it would have been 15,000 second. It would have been, we're looking at meters in 3,000 seconds. So this would actually represent, because remember, he mislabeled it. This is supposed to be our seconds. So to improve his table, the number one thing he could do is label it. By labeling it, he should know that the 3,000 should have been over here. So let's look at Priya. So Priya can bike 150 meters in 20 seconds. So just like those testing strategies, underlining our key points is really important. At this rate, how long would it take her to bike 3,000 meters? So again, distance and time. So let's put our distance here and our time right here. Always label distance, time. So we have our distance of 150 meters by 20 seconds. Now I need to find out how much is going to be in 1 second. And so it's important we're going to be moving down. So I know we're going to be looking for the 3,000 meters. However, we need to find out our unit of 1 second goes how many meters. So if we cut this in half, so our distance of 150, and we're going to divide that by our 20 meters. That is one way you can do it. You can divide 150, that distance over time. Distance over time. Say that 5 times. Distance over time. Because that's how you divide it out. 150 divided by 20. So knowing that, I know that we can go 15 meters in 2 seconds. Wait, how did you get 2 seconds? Well, look, I took off the zeros. So we'd have 15 meters in 2 seconds. But I need to find out how to get to 3,000. 3,000 meters. In how many seconds? We don't know yet. So there's multiple ways you can do this. You can find our 3,000 and we can divide it by our 15. And then multiply that by 2. So I'm going to show us. We have 15 meters. Our distance over time. Distance over time. Distance over time. 15 meters over 2 seconds, and we want that to equal, because these are all equivalent, we want them to equal our distance of 3,000 over how many seconds. And here you're going to cross multiply. So 3,000 times 2 is 6,000. And then we're going to divide 6,000 by 15. So this is where we're cross multiplying. So go ahead and hit pause and work that out. Alright, so when you do this, you have 15 goes into 6 0 times. 15 goes into 60. Well, I know 15 plus 15 is 30. And 30 plus 30 is 60. So 15 goes into 60 4 times. And that comes to 400. So our answer here, change my color, is 400 seconds. So Priya can bike 3,000 meters in 400 seconds. So Pri's neighbor has a dirt bike that can go 360 meters in 15 seconds. So again, we're going to create a table. And what is the first thing we need to do? What is the first thing we need to do? What was the mistake that we made? Well, not we didn't make, but Han made on his. He did not label it. So we always need to label our distance and our time. Distance and time. So our distance is 360 meters. Our time is 15 seconds. Distance over time. 360 divided by 15. Work that out. 360 divided by 15. So 360 divided by 15 is what? It is going to be 24. And that is our distance of meters in 1 second. So we'd have 24 meters in 1 second. Now let's look back at our question. At this rate, how long would it take for them to ride 3,000 meters? So we need 3,000. We need to find the time. So how would you work it out? $3,000 meters. What you're going to do is you're going to multiply 3,000 times 1, which is 3,000, and divide by 24. Go ahead and hit pause. But Miss Nishikawa, how did you know to divide that? So we have distance over time, right? Our distance of 3,000 over what we don't know needs to be the same as 24 over 1. So you cross multiply 3,000 times 1. Divide that by 24. And you get 125 seconds. Hit play. It's freezing up on me. So now we're going to talk about the International Space Station. Can you name 2 things in our town of Greensboro or High Point or wherever you live that are about 1 kilometer apart? How long do you think it would take you to walk 1 kilometer? What might be a typical speed limit on a highway in kilometers per hour? So I know we're used to talking about miles. We run a mile, we go miles per hour. So think about a kilometer. Is a kilometer larger or smaller? So a kilometer is smaller. It's smaller than a mile. So if it is less than a mile, Name two things that are about 1 kilometer apart. So something a little bit less than a mile apart. I know I live in Jamestown near City Lake Park, and it is a little bit less than a mile to go to from City Lake Park to Food Lion. That's about a kilometer apart. So I think it would take, it takes me about 10 minutes, maybe 15 if I'm walking slow with my kids and we're taking our time to walk a mile. I'm thinking it's going to take me less time to walk a kilometer because it's not as far. There's going to be less time than it would take me to walk a mile. So I'm going to say it's going to take me about 8 to 10 minutes. What might be a typical speed limit on a highway in kilometers per hour? So I know on the highways around here, I drive about 65 miles per hour. And if a mile is really far and it takes me, I can go 65 of these in an hour. If they were smaller, I'm actually going to cover more of them. So the kilometers, a typical speed would be about 100 kilometers per hour, which would be about the same as 65. So, in the International Space Station, it orbits around the sun. No, take that back. It orbits around the Earth, not the sun. We orbit around the sun. It orbits around the Earth at a constant speed. So, obviously, you're not in my classroom, so I can't give you a double number line or a table. So, we're going to talk about both. We're going to complete the parts that we can figure out and share it with our partner. So, first, let's look at a double number line. I'm looking at this. What information do I have? I don't have a lot. That makes it a little bit of a challenge because I really don't have a lot of information. I know this is 5. Then I can count 4, 3, 2, 1. So I know this is 1. So 5, 6, this is 7. 8, 9, this is 10. Let me go back and look at my other question. So the ISS, the International Space Station, travels at 8 kilometers per second. 8 kilometers per second. So here's our elapsed time. 0, 1. So here's per second. Remember that word per. So we go 8 kilometers per second. So if this is 8, then we move up 1, 2, 3, 4. We need to do this in increments of 8. So we go 8 to 16, to 24, 32, to 40. So now I want you to find this one. Hit pause. Remember, we just did plus 8, plus 8, plus 8, plus 8. We get to 40. I hope you've paused and you found our missing one right here. Our missing one is 56. Because we have 40 plus 8 would be 48. Plus another 8 would be 56. Now find our last one. And it's 80. Another way you could have done this. We know 8 over 1 these equivalent fractions, would be what over 5? And then we cross multiply. 8 times 5 is 40. Let's see if I can change my color. Okay. So let's talk about here. We knew that this was number 7. So we know our rate of 8 to 1, which is 8 kilometers per second. 8 kilometers per second, 8 over 1. Distance over time. And we want that to be equivalent to our time, our distance that we don't know, for our time, which is 7. So 8 times 7 is 56. And then we do the same thing down here. 8 over 1 has to equal what over 10? 8 times 10 is 80. Challenge yourself a little bit. What would 11 be? Hit pause. Solve it. When you've solved it, hit play. Our answer would be 88, because we'd have the 8 over 1 is equal to 11 times 8, because we cross multiply. We get 88. So let's look at this as a table. So our distance traveled, we start out as 0, elapsed time. We know that we're going 8 kilometers per second. Here we have 80 to 10, our distance to time. Distance over time, 80 to 10. So what are some other representations we can put here? You have 40 for the distance traveled. I might put 7 here. And so no matter what you're trying to work out, always use distance over time. We know it's 8 over 1. And we want it to equal distance of 40. We know 40 over the time. We don't know what that is. So 40 cross multiply times 1 is 40 divided by 8 is 5. And do the same thing, distance over time. Always make your ratios distance over time. Our distance traveled of 8 over 1 is going to be our distance, which we do not know in this case for the second one, over 7 seconds. 8 times 7 is 56. Divided by 1 is 56. So you may find the table is an easier method. You may find the number line is easier. So again, just looking at our numbers, you can see our table as well as our number lines. So what I want us to remember, always include our labels on our tables and our number lines. It's easy to get confused. And remember, we're always doing distance and time. Distance over time. Distance over time. I hope you go to sleep tonight thinking distance over time, distance over time. So for our cool down, what I want you to do is use a sheet of paper and use our strategies of either a table or a double number line. Try the table. I think the table might make things a little easier. Draw your table out. What is the first thing we do with a table? Hit pause and I want you to solve this. First thing, you label it. Distance over time. Always label distance over time. Distance, time, distance, time, distance, time. So in a sprint to the finish, a professional cyclist, that means they are riding a bicycle, travels 380 meters. Well, there's our distance, meters. 380 in 20 seconds. Time of 20 seconds. At that rate, how far does a cyclist travel in 3 seconds? So we know we need to find a 3-second time. We need to find what distance, how far. It's the distance. How far do they travel in 3 seconds? Well, distance over time, distance divided by time, distance divided by time. I hope you say that in your sleep. So we have distance of 380 divided by time of 20. What is that going to be equivalent to? So I'm going to stop here. I want you to solve it. I want you to solve it. Remember, we need to find our 1 second, in case you're stuck there. All right, I can't wait to see your answers. I hope that this helped, and I'll see you in class.